all of you are eyeing the NEET exam, which is being scheduled on 12th of September, right? So that is why the practically has brought exclusive or NEET crash course for the next 20 days for the chemistry, where you will learn or you will understand how to solve the different types of questions which has been asked in a NEET exam previously. Okay, so good afternoon everyone. My name is Mayur. Let's start the session. Okay. Good afternoon everyone. As you all know, nature of chemical bonding has the theories for the theories of different types for the bond formation. One of those theory obviously is overlapping theory. Another is what? Another is hybridization theory. What does overlapping theory says? It was presented by Hitler and London, not that Hitler from the Germany. Okay, this is the name of another scientist. It was presented by Hitler and London to explain how a covalent bond is formed. What are the main points of theory? See, to form a covalent bond, overlapping occurs. To form a covalent bond, overlapping occurs between half-filled valence shell orbital of two atoms. For example, if you have a hydrogen should look like this. Nucleus here, electron here. Then the another hydrogen that is also having a nucleus here, electron here. So both of these overlap like this, where the electrons would be here, nucleus would be here. That is how you form the H2 molecule. Okay, so that is what this theory says. The resulting bond acquires a pair of electrons with opposite spins to get the stability. You can see here the resulting bond, this resulting bond is having two electrons in an opposite direction. One is in a upward direction, another is in a downward direction. Now, orbitals come closer to each other. Orbitals come closer to each other from the direction in which there is a maximum overlapping. So orbital always comes from that direction, which gives you a maximum overlapping. Okay, that is how the bond formation happens according to overlapping theory. Okay, then we have one more theory, hybridization theory, but we will see that once this finishes. So covalent bond has a directional character. We all know that. Okay, in your studies from last 2 years, you must have understood that covalent bond has a directional character, whereas ionic bond do not have any directional character, because ionic bond does not involve overlapping of atomic orbitals, whereas covalent bond involves overlapping of atomic orbital, which gives them ultimate direction. Okay, next, extent of overlapping is directly proportional to the strength of a chemical bond. That means stronger or larger the amount of overlapping, stronger will be the bond, and vice versa. That means the strength of a chemical bond will be decided by extent of overlapping. That is why they are saying extent of overlapping is directly proportional to the strength of a chemical bond. Now, extent of overlapping depends on two factors. There are two factors which decides it. First is nature of orbital. That means which orbital are overlapping together. For example, if you have a P, D, F, these three are directional orbital. P, D, F are directional orbital. This shows more overlapping. Mind this, okay? This will come handy to you when you are solving the objective questions from this chapter. Okay, so what I'm saying, the nature of orbital PDF are directional orbital. That is why this shows more overlapping. S orbital is non-directional, and since it is non-directional, it shows less overlapping. So the bottom line is that the directional orbitals, which are PDF, shows more overlapping, and S orbital, which is non-directional, shows less overlapping. Okay. Next, nature of overlapping. Now there are two types of overlapping. One is coaxial, another is collateral. Now coaxial means what? Along the axis. Coaxial means along the axis. For example, this is your p orbital. Okay, this is its axis, right? That is what its axis. Then you have another p orbital. This p orbital also has this as a direction. So if they overlap in this direction, that means if they overlap like this, so this is called as coaxial overlap. And this overlap, you can see here, overlapping is more here. Overlapping is more. It is like this. You can look at my hand. It is like this. So you can see this overlapping is more than this overlapping. This overlapping which I'm telling you right now, this is lateral overlapping, or I would say collateral overlapping. Let me show you how it looks like. This is your collateral overlapping. This is collateral overlapping. And you can tell me by your experience, this overlapping is strong or this overlapping is strong. Obviously, this overlapping is strong. Okay, that is how, and that is why the coaxial overlapping is stronger. It gives you sigma bond. It gives you sigma bond. And this collateral overlapping, you can see here, the extent of overlapping here is less. Extent of overlapping here is less. This gives you pi bond. Extent of overlapping is less. It gives you pi bond. Okay. So the bottom line is coaxial overlapping has extent of overlapping more. It gives you sigma bond, which is stronger than the pi bond. Collateral overlapping, extent of overlapping is less. Obviously, it gives you pi bond. And always remember, sigma bond is stronger than pi. Lastly, order of strength of coaxial overlapping. Now, among the coaxial overlapping also, there is a certain order of strength. Okay, what is that order? See, whenever two orbitals are there which are overlapping, more the number of directional orbital, more is the overlap. As simple as that. What I'm saying, whenever you are getting two coaxial overlapping orbital, you just need to remember, more the number of directional orbital, higher will be the extent of overlapping and stronger will be the bond. Okay, if you look at the first option, PP, both are directional. Okay, that is why the extent of overlapping here is highest. In SP, you got only one directional, which is P. S is not directional. We had seen that, because of which SP comes second. And last, SS, where you have got no directional orbital. And that is why the extent of overlapping is shown in the following order: PP, SP, and then SS. Okay. So moving ahead, overlapping theory. See, as I already shown you there, this is PP overlap. This is strongest. Then you have a PS or SP overlap. This is second number. Then you have a SS. Okay. More the number of direction. See, higher the number of directional orbital, stronger will be the overlap and stronger will be the bond. That is why you can see there PP, SP, and then SS. Okay. That is with the overlapping orbital. Now, as the value of n increases, the bond strength decreases. That means, suppose if you have 2s and 2s, if you have 2s and 2s, it would overlap like this, right? No problem with that. But if you have a 3s, now obviously the size of 3s would be larger than 2s. Okay, so now they are going away from the nucleus. I would say the extent of overlapping becomes less. Why? Because the bond length increases, right? As the number of that n increases, the bond length increases. As the bond length increases, you know that the force of attraction between the two nuclei decreases. When that happens, obviously the bond strength would or has to decrease, and that is why as the value of n increases, the bond strength decreases. Okay, you can clearly see here 1s 2p. So 1s 2p, the n is smaller, then you have 2s 2p. Now in 2s 2p, why it is weaker than 1s 2p? Because in both these cases 2p 2p are constant. Then what is deciding factor? 2p is not a deciding factor. Now the deciding factor is 1s. Here it's 1s, here is 2s. And now you know that between 1s and 2s, 1s would form a shorter bond. And shorter bonds are stronger than the longer bonds. Why? Because the distance between the nuclei is less. If the distance is less, the force of attraction, which is also called as a bond, the force of attraction is higher. Okay. And lastly, 3s 3p. If n is same, then you need to follow this order, which we had already seen, right? If n is same, then you need to look at the orbital. Higher the number of directional orbital, stronger will be the bond. So you have pp here, that is why it is the highest. Then you have sp, lastly you have a ss. So the bottom line of overlapping theory is that higher the number of overlapping orbital, higher will be the extent of overlapping, stronger will be the bond. That is when n is same. If the n is different, then the overlapping orbital which is having a smaller n would have a high extent of overlapping more, and hence they will be having a stronger. So that is what overlapping theory tells you in overall. Okay, sure. Moving ahead. So this overlapping theory is telling you how sigma bonds have been formed, which I have already told you. This has been formed by pp coaxial overlapping, right? Then you have 2p orbitals. 2p orbital overlapping laterally or sideways. 2p orbital overlapping laterally or sideways to form a pi bond. You can see that here. Okay, that is how these bonds are actually formed. Okay, moving ahead. How the delta bond is formed? The delta bond is a special type of bond which has been formed by lateral overlapping of 4 lobes of d orbital. It is a special type of a lateral overlapping in which all the 4 lobes of d orbital overlap laterally with other similar d orbital. Obviously that bond is called as delta bond. Here you have dx square dash y square. That means if this is your x, this is your y, the orbitals has to be like this one, and then you got another x and y which looks like this. So this and this overlap laterally. That means this overlaps with this overlaps with this. Okay, I cannot show you because this is in 2D. They are actually overlapping in 3D. See, if you take that side of xy, it should look like this, 4 orbital, and from this side 4 orbital, and then they are overlapping like this laterally. So this type of lateral overlapping, when it happens with the d orbital, especially dx square dash y square with another dx square dash y square, then the produced bond is called as delta bond. Okay, chalo, moving ahead. Chemical bonding, let's see some of the questions now. Now with the questions we will cover the many concepts of chemical bonding. Okay, now the very first question, when 2s 2s 2p 2p 2p, 2s. Orbitals overlap, the bond strength decreases in the order. Now we just now had seen the overlapping theory. And what did I tell you there? That whatever overlapping orbitals are there, the option which is having the higher number of directional orbital will having the more extent of overlap, and hence it will also have the bond strength higher. Okay, so if you look at all the option, the pp is higher, we know that. Up, so this has to be the first, pp has to be the first. After pp it has to be sp or ps, whatever you call it, doesn't matter. pp, sp, and then lastly you have a ss. So directional orbital do, if I talk about, here there are two directional orbital, here you got only one directional orbital, here you got zero directional orbital. And which option suits this? The second option, B, where you have pp first, then ps, that means sp only, and lastly you got ss. That is why option B is the correct answer for this. Next, number of sigma and pi bonds present in the following compound. How many are there? Let's write the structure. C H H H, then you have a CH here, double bond, CH, another CH, sorry, this is not another, 1 2 3 4, yeah, this is not CH, then triple bond CH, right? That is how it is. Let's see how many sigma are there. So this is sigma, 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 this also sigma, this also sigma. Let's count how many are there. 1 2 3 4 5 6 7 8 9 10. There are 10 sigma, right? And how many pi are there? This one is pi, right? Then you got 2 pi here, this one, this one. So basically you have a 10 sigma and a 3 pi. Always remember, whenever you have a double bond between two elements, the first bond is always sigma, the second bond is pi, third bond is also pi. If you have a fourth bond also, that is delta. That is how it is. So first bond is sigma, second bond is pi, third bond is pi, fourth bond is delta. In our option we got one triple bond, one double bond. So each triple bond will have 2 pi and another double bond has 1 pi. So together we have 3 pi and 10 sigma. And that is why the option A suits this. That is why our answer has to be this one. Okay, sure. Moving ahead. Hybridization theory. Now what hybridization theory tells you? That, see, hybridization theory and VCP are theory, this and MOT also. These three are the theory which will be giving you maximum number of questions from this chapter. Okay, the number of hybrid orbitals on a central atom of a molecule or ion is always equal to number of sigma bonds plus lone pair of electrons. How can you do that? Let me tell you. Suppose if you have a CH4, now in CH4 carbon has formed 4 sigma. There are 4 sigma, and how many lone pairs are there? 0 lone pair. So which makes your N is equal to 4. So if the N is 4, hybridization has to be sp3. If your N is 3, hybridization is sp2. If your N is 2, hybridization has to be sp. If N is 5, hybridization is sp3d. If your N is 6, hybridization is sp3d2 or d2sp3. If the N is 7, hybridization has to be sp3d3, like that. So that is how whatever number you get, from that number you can find out the hybridization. Okay, single element, one element can represent many hybridization states depending on experimental condition. For example, carbon shows sp hybridization in alkyne, it shows sp2 hybridization in alkene, it shows sp3 hybridization in alkene. So that means carbon can show different types of hybridization depending on the conditions. Okay. Hybrid orbitals are differentiated as sp, sp2, sp3, that you already know, right? The directional properties, the directional properties in hybrid orbitals is more than the atomic orbital. As we had seen earlier in the overlapping theory, that the orbitals having higher directional property can overlap more effectively, and it does overlap more effectively, giving you a stronger bond. And now your hybrid orbital has extra, or I would say it has more directional property. So the directional property in hybrid orbitals is more than atomic orbitals, and that is why hybrid orbitals form stronger sigma bonds. Always remember, hybrid orbitals form stronger sigma bond, and the orbitals which do not undergo hybridization, they form pi bond. The orbitals which do not undergo any hybridization forms pi bond. The orbitals which undergo hybridization, they forms sigma bond, stronger sigma bond. Again here, the directional property of a different hybrid orbitals will be in the following order. Now again, as I told you earlier, higher the number of directional orbital, stronger would be the overlap. Again, directional orbital D. In sp3d3 you have p as a directional orbital and d also is a directional orbital. We had seen that. So out of 7 you got 6 directional orbital. Here you got 5, here you got 4, here you got 3, 2, 1. So in sp3d3 the directional orbitals are more than sp, because of which sp3d3 will form a stronger bonds than the sp. Okay. Now hybridized orbitals can also show axial overlapping to form a sigma bond. Okay. Now hybridized orbital do not form a pi bond. Hybridized orbital, as I told you, they are directional, right? They are directional like this, and whenever the one lobe of hybrid orbital is overlapping, the another lobe shrinks. For example, suppose this is your orbital which is overlapping, and suppose from this direction it's overlapping, then what happens? This direction stays as it is, but the other lobe of that overlapping orbital, it gets shrink like this. It gets shrink, because of which this hybrid orbital gets extra directional character. And since they have extra directional character, they can only overlap through their heads. Now, since they can overlap only through their heads, they can only form a sigma bond. That is why hybrid orbitals do not form a pi bond. Pi bond is formed by the orbital which has not undergone a hybridization. Okay, remember this, all of my words. Now, type of hybridization. Now we already know the type of hybridization that we have in a carbon: sp in alkynes, sp2 in alkenes, sp3 in alkanes. Okay, so here we have to see only another types of hybridization, which is sp3d. Now if you look at the ground state hybridization of phosphorus, here you have a neon. Neon has how many electrons? 10, right? Now atomic number of phosphorus is how much? It's 15. So you have neon which is 10, then 3s2, 3p3, 3d, 0. So you do not have any electron in d orbital. Okay. Now phosphorus has to form a 5 bond here, right? But if you look at this, your phosphorus has only 3 unpaired electrons. Now to form a 5 bonds, it should have 5 unpaired electron, and that is why one of the 3s electron gets promoted to empty 3d orbital. Now this 3d orbital is dz square in this case. Okay, it is dz square. Now it gets promoted. Now it has 5 unpaired electron. Now these 5 orbitals overlap together to give you 5 sp3d orbitals. You can see here sp3d, 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 sp3d. Now chlorine comes with its p orbital and overlaps with phosphorus to give this shape. This is called as trigonal bipyramidal shape. Okay, trigonal bipyramidal. Trigonal bipyramidal. This is trigonal. One pyramid above, one pyramid below, and then there is a formation of a pyramid. That is why this shape is called as trigonal bipyramidal. Okay, moving ahead, sulfur. Sulfur is forming SF6, right? That means sulfur has to form 6 bonds. If you write the electronic configuration of sulfur, its atomic number is 16. So you have a neon here, neon 3s2 3p4 3d 0. So you got only 2 unpaired electron here, right? But sulfur has to make available 6 unpaired electron. So what does it do? It promotes this first pair of electrons in 3p. Now this pair goes from here to here. That is your first excited state. Okay, I have not shown you your first excited state here. So you get the, after promoting this electron, you get the 4 unpaired electron. But since we needed how many electrons? 6. So in the second excited state, this electron pair from 3s, it also gets promoted here. And now you have 6 unpaired electrons. So this 1s, 3p and 2d, all of them together overlaps to give you sp3d2. You get 6 sp3d2 hybrid orbitals. They have been expanded in this shape. That shape is called as trigonal. Sorry, you can't call it as trigonal. Sorry, it's an octahedral shape. See, it is like this. Then you have a fluorine here, and then you got a fluorine here. So that is how you get a octahedral SF6, where each sulfur undergoes sp3d2 hybridization. It produces 6 sp3d2 hybrid orbitals. Each sp3d2 hybrid orbitals then overlaps with the p orbital of fluorine to give you 6 sp3d2 p sigma bonds. Why I am saying p? Because from fluorine p orbital is coming, and from sulfur sp3d2 orbitals are coming. That is why the name of that sigma bond is sp3d2 p sigma bonds. Okay, chalo, moving ahead. Now we will be having only questions after this. Okay, we have covered most of the theory part. Okay, whatever theory we have been, we remain other, whatever theory we are still yet to cover, that we will be covering through the objective questions only. Okay, now what is the correct order of bond angles? NH3 H2O. Now we know that NH3 has bond angle around 107 degree, right? H2O has bond angle around 104.5 degree. So NH3 has higher than H2O, that's for sure, right? Then you have a PH3. In PH3, the bond angle is somewhere closer to 90 degree. I won't say it is exact 90 degree, but it is somewhere around 94 degree. Okay, if you're talking about lastly H2S, for H2S, the bond angle literally is close to 90 degree. That is why NH3 higher than H2O, H2O higher than PH3, PH3 higher than H2S. That has to be your right answer. And where is that answer? NH3, H2O, PH3. Yes. That is why the first for this question, answer A is the correct answer. Next, the correct increasing bond angle. The correct increasing bond angle among BF3, PF3, ClF3 follows the order. Now for BF3, this is how shape of BF3 is. For BF3, hybridization is what? It's sp2, right? For PF3, hybridization is sp3. For ClF3, hybridization is sp3d. Now BF3 shape is trigonal planar because hybridization is sp2. Therefore, bond angle is how much? It's 120 degree. So it is 120. Then you have a PF3. Then you have a PF3. For PF3, since it is sp3, it should look like this. You have a lone pair here of phosphorus. Then you have a fluorine. It is like this. It is trigonal pyramidal, or I would say it's a trigonal, not exactly trigonal planar, but yeah, you can say it's a trigonal pyramidal. You have a pyramid here. So sp3 bond angle, it obviously has to be less than the 120 because it is sp3, so it is somewhere hovering around 109 degree. It might be slightly lesser than 109 degree or might be slightly higher than 109 degree, but it cannot distort too much from 109 degree here. Then you lastly got ClF3. ClF3 has sp3 hybridization, but if you look at its shape is like this. This is fluorine, this is fluorine, and this is fluorine. It's a T shape. And then you got what? Then you got lone pairs here. These are two lone pairs here. So this is your trigonal. And then you have pyramid also. But we do not consider the lone pair in the shape. In the geometry, you consider the lone pair. But in the shape, you do not consider the lone pair. So what do we consider is only fluorine and fluorine. And if you look at this compound, it is T-shaped. It is T-shaped. Now what they ask us is bond angle. How to write the bond angle? Bond angle is FClF. They're asking this. So you can see this bond angle is, it is less than 90 degree. It is not exact 90 because had this fluorine, chlorine and fluorine, had it been like this, it would have been 90 degree. But this fluorine is slightly bent like this. It is slightly bent, because of which this angle is lesser than 90 degree. And that is why what is the correct option here? See, this is the correct option, C. You have a BF3 which is 120, PF3 which is closer to 109 degree, and ClF3 which is closer to 90 degree. That is why option C is the correct. So correct order of bond angle is ClF3, PF3 and BF3. Okay, you should be able to know how the shapes of different molecules are and what could be their possible angle for you to be able to solve all this type of questions very easily. Okay, so but I will tell you the tricks as we go on the way. I'm going to tell you the tricks, so don't worry about it at all. Okay, chalo, moving ahead. Next, among LiCl, RBCl, BeCl2 and MgCl2, the compounds with greatest and the least ionic character respectively are. Now you got chlorine everywhere. Okay, apart from chlorine, what you have? You have a lithium, sodium, potassium, rubidium. So position of rubidium is this. Position of lithium is this. Then then neighbor of lithium is what? It's beryllium and it's magnesium. Okay, always write in this format. Why I'm writing in this format? Because if you write in this format, it can tell you what would be the size of your cation is, because the size of cation will decide here whether it will be having a more ionic character or less ionic character, because anion is constant here. In all these cases, anion is same. If the anion is same, anion is not going to be deciding factor. Deciding factor is going to be cation, and we know that the percentage ionic character, is directly proportional to size of a cation. It is directly proportional to size of cation. That means larger the size of cation, higher will be the ionic character, which makes RbCl to be most ionic. And we know that as we go down the group, the atomic size increases. As we go down the group, atomic size increases, which makes rubidium to be largest in size here. Now this is with the most ionic compound. Okay, so that is for sure. Now what we need to do, the least ionic character. Now as you know, the percentage ionic character is directly proportional to the size of cation. So in all these four options, the largest cation will have a most ionic character, and vice versa. Vice versa means the smallest cation would have the least percentage of ionic character, obviously. That means the smallest cation will have more percentage of a covalent character. If it would have a more percentage of a covalent character, obviously it would have a less percentage of a ionic character. So if you look at all this cation, which cation is smallest in size? Now many of you might think it's a lithium. No. See, if you're talking about rubidium and lithium, yes, lithium is smaller, rubidium is larger, but that is for the particular group. If you're talking about period, when you are going from left to right, whenever you're going from left to right, the size decreases. That means beryllium is smaller in size than lithium, and magnesium and beryllium, since they are belonging to the same group, and magnesium is in the next period of beryllium, magnesium has to be larger in size than beryllium. Magnesium has to be larger in size than beryllium, which makes beryllium smallest cation here. If the beryllium is the smallest cation, it would surely have the least ionic character. And that is why our options are RbCl and BeCl2. And that is why our answer is this B, RbCl, BeCl2. That means option B is the correct answer for this. Okay. Moving ahead. PCl5 exists, but NCl5 does not exist. Why? For this, we might need to go 2 or 3 slides behind. We had seen there that phosphorus overlaps with the chlorine from all the 5 sides. Remember, hybridization of that was Sp3D, and the shape was Trigonal Bipyramidal. Okay, why phosphorus was able to do that? Okay, shall we go to the previous slides? Let's go look at it. See, your phosphorus has here empty d orbital. Your phosphorus has here empty d orbital, where this electron from S could be promoted which gave rise 5 unpaired electron, and ultimately that gave us 5 sp3d hybrid orbitals, which then overlapped with p orbital of a chlorine atom. That is why pCl5 could exist. If you're talking about NCl5, the atomic number of nitrogen is 7, and for nitrogen there is no empty d orbital. Absence of empty d orbital, it is actually absent here. In fact, you might ask then why phosphorus has empty d orbital. See, starting from aluminium atomic number is 13. So from aluminium, every element has d orbital. Now that d orbital could be empty, it could be partially filled, it could be half filled, it could be almost filled, or it could be completely filled. That's a different thing. That will depend on your atomic number, ultimately on the electronic configuration and the stability. Okay, those are the things that will decide it. But counting from aluminium, it will surely have at least empty d orbital. So aluminium has empty d orbital, silicon has empty d orbital, phosphorus also has empty d orbital. Okay, then you might see, ask then why nitrogen does not have empty d orbital. See, nitrogen is belonging to the second period. Okay, phosphorus, sulfur, aluminum, these are belonging to the third period. Now carbon, nitrogen, oxygen, fluorine, all of these four, they are belonging to the second period. Let me write it here. Starting from boron actually. Okay, boron, aluminium. Oh, sorry. Let me write it. Where should I write? Okay, write it here. Boron, carbon, nitrogen, oxygen, fluorine. Then you have aluminium here, silicon here. For nitrogen you have phosphorus, for oxygen you have sulfur, for fluorine you have chlorine. So all of this and below you will have a empty d orbital always. But boron, carbon, nitrogen, oxygen, fluorine does not have empty d orbital. The thing is that they do have empty d orbital. Okay, they do have empty d orbital, but the thing is that their electron count is around 2p orbital only. So after 2p, see, d orbital can only start from the third quantum number only. That means for phosphorus or boron, carbon, nitrogen's electrons to go to the 3d orbital, they need to go beyond 3s, which is empty in all of these elements, because for fluorine atomic number is 9. You have electronic configuration 1s2, 2s2, 2p5, right? So after 2p6 gets completed, then you will have 3s, then 3p, and then 3d. So you are getting my point. All these second period element, they need to go to the 3s first, then 3p, and then 3d, which makes 3d to be very high in energy from them. And that is why their electron cannot promoted to that higher energy level. And that is why in summary we says that they don't have an empty d orbit. Okay, so that is why the reason for that NCl5 does not exist, because nitrogen has no vacant 2d orbit. Now 2d as such doesn't exist, by the way. 2d as such doesn't exist. Okay, it is always 3d. Okay, so I hope you must have got this, you must have enjoyed it. Okay, so moving ahead. Now, among the following species, the isostructural pairs. Now what is mean by isostructure? Isostructural pair means species having same structure. The species having a same structure is called isostructural. Species having same number of electrons are called as isoelectronic. But you can see the name isostructural. Okay, iso means equivalent or same. Structurally structure. So the species which are having same structures are called as isostructural. Now we know that structures can be predicted from your hybridization schemes. Okay, so NO3 1 minus. Let's find out the hybridization first. NO3 1 minus look like this. N double bond O, O minus, O minus, you have plus here. So this plus and minus cancels out together and 1 minus remains there. That is why you have a charge of 1 minus. How many sigma bonds are there with the nitrogen? Let's find out its hybridization first by using our trick which I have taught you earlier. You got a sigma bond here, sigma bond here, sigma bond here. This another bond is pi bond. And does nitrogen have any lone pair here? No lone pair, right? No lone pair, 3 sigma bonds. So 3 sigma bond, that means hybridization has to be sp, and the shape is trigonal planar that I have already drawn here. You can see that. That is for NO3 1 minus. Then you have a BF3. For BF3, the boron already has formed 3 sigma bonds. And boron never has a lone pair. In fact, it has empty orbital. So this is also trigonal planar. Hybridization is also sp2. So both these structures are same. That means NO3 1 minus and BF3 are isostructural. Where are they? See, there are two options. One is C, another is B. Okay, so it could be B or C. It's like a playing KBC now. Now we know that for sure that A is not an answer. D is also not an answer. So what we are remained with? B and C. Now we need to look at the other things. H3o plus. What is the hybridization of H3o plus? If you write oxygen, hydrogen, then you got 2 lone pairs. That is your water, right? Now, how do we find out the hybridization scheme? Number of sigma bond. How many sigma bonds are there? This sigma. You got 2 sigma. How many lone pair? 2 lone pairs. So total n is equal to 4. If the n is 4, hybridization has to be sp3. Hybridization has to be sp3. Okay. Now if it is sp3, its shape is, we know that it's a V-shaped molecule, right? You know that we don't consider this lone pair in the shape. So if you look at this shape, it is V-shaped. Now another one is HN3. How does HN3 looks like? HN3 shape actually is like this. N double bond N, double bond N. You have a plus charge, you have a minus charge here, then you have another minus charge. That is your plus minus gets cancelled. You got N3 1 minus. N3 1 minus counterbalanced by H plus. Okay, that is how it is. So if you write its structure, oh, there is confusion here. Let me tell you one more thing. This is not HN3. Okay, let's rub it down. It is NF3. Sorry, my bad. I don't know. Option might have been put in a wrong way there. That wasn't a thing. NF3. We were actually talking about NF3 and H3o plus. So this is the shape. Okay. Now H3o plus, what happened? This lone pair gets donated to the H plus ion. And that gives you what? That gives you H3O1 plus. So that means H3O1 plus should look like this. This is the oxygen. Oxygen has, let me write it here. Oxygen has got 1 lone pair. Okay. and 3 hydrogen like this. So the shape again is a trigonal pyramid. That is how your H3O1 plus look like. Hybridization is sp3 and NF3. NF3 is just like NH3 only. You got lone pair here and 3 fluorine atoms are like this. It is also sp3 and it is also trigonal planar. This is also trigonal planar. So H3O plus and NF3, they are isostructural, and that is why the correct answer is NF3 H3O plus NO3 minus PF3. That is why our answer is C. If you are talking about HN3NO, which I had drawn here, its shape actually is like this. It's a linear shape. See, and minus plus this nitrogen is attached to hydrogen. You can see here sigma bond, central atom. We are talking about central atom, right? Sigma bond, this is pi, this is pi. So 2 sigma, no lone pair, right? 2 sigma, no lone pair, that means number is 2. So hybridization has to be sp. If it is sp, it's a linear. And did you see any other compound here which is being linear? No. And that is why we cannot include HN3 here. Okay. That is how you can solve these isostructural related questions. Moving ahead. An atom of element A has 3 electrons in its outer shell. That means A has this inert gas core outside which it has 3 electrons. We don't know where 3 electrons are there, but anyways 3 electrons, they are saying. B has 6 electrons in its outermost shell. So your B should look like this. B is equal to again inert gas core and you have a 6 electron, right? Now how can we find out the valency? Now we know that if there are 2 electrons being added to the B, it will have 8 electrons, right? That means B can show valency 2. It can show valency 2. And as far as A is concerned, you got 3 electrons outside inert gas core. That means your A can lose 3 electrons and it can show valency 3. Okay. So valency of A is 3, valency of B is 2. Then how can we justify this? By cross multiplying. That means you need to have 2A and 3B to be able to form a compound between them. Because if you count this, valency of A is 3, we have taken 2A, right? So 3 into 2, valency of B is 2, we have taken 3B, right? So that means valency 2 into 3. This is also 6, this is also 6, because both of them has to be same, right? But their valencies was different. That is why we needed to cross multiply. That is why the correct answer is A to B3. Where is A to B3? Here. A to B3. That is why B is the answer. Okay. Next. 2 element X and Y have following electronic configuration. X has 1s2, 2s2, 2p6, 3s2, 3p4, 3p6, 4s2. So this is your inert gas core. You can see clearly that there are 18 electrons. Therefore, your X is equal to argon. Outside it, it has 2 electrons. Actually, it's a calcium. Okay. That much you will also know now. Then you have a Y. 1s2, 2s2, 2p6. This is your inert gas core, that is neon. Outside it, it has 7 electrons, 3s2, 3p5. Total electrons are how many? 7. So you know that this is chlorine, right? So no need to pretend that you don't know what it is, right? It is calcium, it is chlorine, we know that. Valency of calcium is 2, and valency of chlorine is 1. So the compound can be formed from them, could be Ca, Cl2, and that is why it has to be XY2. XY2, option A, right? Sometimes it is quite easy. From the electronic configuration, you can immediately find it out that what could be the compound formed from them. Okay, no need to go by this electronic configuration. That might make things a bit complicated. Okay, so moving ahead. The correct order of oxygen-oxygen bond length in O2, H2O2 and O3. See, since we are in the structure, when we are in the chapter called chemical bonding, every now and then you should be able to reproduce the structure again and again, along with its hybridization scheme, along with its bonding pair, lone pair, okay, because that will only tell you the other things about it. Now here they are asked the bond length. Okay, so let's draw it. Oxygen, you have a double bond in O2, right? Then H2O2. H2O2 you have like this. So this is double bond. So bond order or bond length is what? Bond, let's see bond order. Bond order means number of bonds, right? Here bond order is 2. Here bond order is 1. Then you have ozone. So ozone structure is like this. O double bond O minus. And you have a plus charge here. Here there is a continuous resonance. Negative charge goes here. This bond breaks. Electron goes to this oxygen. What does this gives you? O minus single bond, doubly bonded O plus charge. So basically these are two resonating structures, or I would say canonical structures, and their correct representation is what? Their correct representation is their resonance hybrid. Resonance hybrid should look like this: O single bond O, O single bond O, and then you will have this dotted scheme. What is this dotted scheme? These are the pi electrons. These are pi electrons which are oscillating between these three oxygen atoms because of resonance. And this thick line you are saying it's a single bond, complete bond, and this dotted line which is pi bond, you can see here this oxygen has formed a double bond here, and this oxygen has formed a single bond here. So in one structure you have a double bond, in another structure you have a single bond. That means the real bond order should be somewhere between double bond and single bond. So if you take the average of it, double bond plus single bond, total bonds are 3. 3 divided by 2, it has to be 1.5. So 1.5 is its bond order, because this single thick line is of sigma bond and this is pi bonded electron, and there you have a bond order 0.5. So 1 plus 0.5 is equal to 1.5. Okay, so bond length. See, whenever you have a smaller bond order, the bond length has to be larger. Okay, because higher the number of bond order, more will be the number of bonds formed between the atoms. More the number of bonds formed, two atoms will be pulled closer. When that happens, the bond length decreases. In other words, let's put it in a different way. Bond order is inversely proportional to bond length. Okay, this is the formula you can remember always, but you should be knowing the reason of that also. That is why your peroxide will have the largest bond length, which was 1. Then you have ozone, which has a bond order 1.5, and lastly you have a O2, oxygen, where bond order is 2. And that is why the correct answer has to be yes, C, H2O2, O3 and O2. That is why your answer is C. Okay, chalo, moving ahead. In which of the following central atom does not use sp3 hybrid orbit? Which of the following does not use sp3d hybrid orbitals? So we know that we had seen in NF3, you got 3 bond pair, 1 lone pair. So this is already sp3. You know that. We had seen in the previous examples that H3o plus is sorry, yeah, H3o plus, this is also a sp3. Okay, now what we remain with BF2, BF3 1 minus and NH2 1 minus. Now NH2 1 minus, you have a 2 sigma here plus 1 lone pair plus you got a negative charge. Negative charge would be treated as a lone pair here. So that means you have a 2 sigma plus 2 lone pair, which makes total count n is equal to 4, and hybridization has to be sp. Okay, that is with the NH2 1 minus. Then BF3 1 minus. Now BF3 1 minus, let's see what could be its hybrid. Now we have arrived to the answer. Obviously all of this B, C, D, they are using sp3. That means BF3 must not be using sp3, right? Then what it is using, let's see. Beryllium atomic number 4, electronic configuration has to be 1s2, 2s2, 2p0, right? So in a ground state, you have a 2 electron in 2s, 0 electron in p, right? What happens in excited state? One of the electron from here gets promoted to empty px orbit. Now these 2 electrons would be overlapping with the fluorine. One fluorine, another fluorine. This one S and another is what? P. So that will give us sp hybridization. Now fluorine will come, they will overlap. So that is how you get BeF2 sp hybridization. Okay? But wait a minute, you have a BeF3 here. Now what does that do? See, whenever you have this BeF2 interacting with the F minus, F minus is bringing its electrons together now. Beryllium does not have any electron. So this fluorine brings the electron to give you BeF3 1 minus. That 1 minus charge is on the fluorine. So what happens here? Fluorine comes and deposits its 2 electrons here. Both the electrons here, F minus. Now you have 1s and 2p. Both of them overlaps to give you sp2 hybrid orbit. That is why BeF3 1 minus has sp2 hybridization. BeF2 has sp, but BeF3 1 minus has sp2. So that is why that is your answer. Okay, answer we have already came to we already reached to the answer, but I wanted to tell you what is the hybridization of BeF3 1 minus and how it was made in that way. Okay, so moving ahead. Next, select the pair of compounds in which both have different hybridization. Select the pair of compounds in which both have different hybridization but have same molecular geometry. That means hybridization is different but geometry is same. So BeF3 hybridization is what? It's sp3. Sorry, my bad. It's sp2, right? In BrF3 you have sp3t, right? So hybridization is different, but is their shape same? Let's find out. BF3 you have this shape, trigonal planar. Okay, BrF3 you have this shape. It is a T-shaped geometry. So that means this is not an answer. Next is ICl2 1 minus. ICl2 1 minus, what is the hybridization of it? If you write the ICl will have a 1 bonding pair and 3 lone pair, right? Like this, because each halogen has how many electrons? 7 electrons. Out of 7, it has used 1 for the bonding with chlorine. Rest 6 electron will remain as a lone pair. So you got 3 lone pair plus 1 bond pair. So N is equal to 4 and hybridization is Sp3. That is with ICl. Okay. But this ICl is added with one more Cl minus. Just now we had seen the earlier case. Remember? With the BCl BF31 minus, where Sp hybridization of BCF2 was converted to BeF31 minus, which has Sp2 hybridization. So here this Cl minus comes and deposits its electron in an empty d orbital of iodine, because of which this hybridization now becomes Sp3d. And what is the shape of Sp3d? Shape of Sp3d always is trigonal, it is always trigonal pyramidal, where you have a lone pair here, lone pair here, lone pair here, and chlorine. One chlorine here, another chlorine here. So this is a shape. If you talk about the geometry, ICl2 1 minus, it is trigonal bipyramidal. But if you're talking about the shape is ICl2 1 minus. Look at this. This is the linear shape, right? Same is the case with the BeCl2. BeCl2 we had seen earlier, right? If BeF2 has Sp hybridization, BeCl2 also has Sp hybridization, because central atom and the number of auxiliary atoms is same. Central atom is beryllium in both cases. Which case? BeF2 and BCl2. Auxiliary atoms, there were 2 chlorine atoms. Here you have 2 chlorine atoms. That means hybridization of BCl2 and BF2 are same, which is Sp, and shape is shape is linear. It has to be linear. That means our answer has to be B, where ICl2 1 minus has hybridization Sp3d, whereas BCl2 has hybridization Sp, but both of them are linear, and that is why our answer has to be B. But apart from that, we also need to look at this BCl3, PCl3, BCl3 and PCl3. BCl3 we had seen its hybridization is Sp2. PCl3 has hybridization Sp3. So hybridizations are different, but shapes are also different. That is why C cannot be our answer. Then lastly, you have a PCl3 and NCl3. PCl3 also has Sp3. NCl3 also has Sp3. So here, what they are asked, which pair was having different hybridization but same geometry. This is having same hybridization. So that means this cannot be answer. The answer is B. Okay. Next, moving ahead, the states of hybridization of boron and oxygen atoms in a boric acid, that means H3BO3R respectively. Now there is a very less space here. We might need to go to the next slide. We can use a space. Let's write the structure of H3BO3 hydroboric acid there. We'll come to know its hybridization also. So H3BO3, this is our OH, OH and OH. So you can look at here, see your boron has formed 3 sigma bonds. It has formed 3 sigma bonds and 0 lone pair. So that means your N has to be 3. So hybridization has to be Sp2, right? Hybridization has to be Sp2. Now let's look at the OH. Boron, oxygen, hydrogen, oxygen, hydrogen, oxygen, hydrogen. Now all these OH are same. So your oxygen has formed 2 sigma bonds. This one is sigma. This one is also sigma. So your oxygen has formed two sigma bonds plus it has two lone pair, which makes the N together is equal to 4. So N together 4. That is why the hybridization of oxygen has to be Sp3 there. Okay, it has to be Sp3. Now let's move to the last. So what they ask, what is the hybridization of boron oxygen atoms in a boric acid? So boron respectively they are asked. Okay, so for boron it's Sp2 and for oxygen it's Sp3, and that is why our answer has to be B. Okay, now next, which of the following option with respect to increasing bond order is correct? Which is the correct bond order here? Now this question is of MOT. MOT is what? Molecular orbital theory. Okay. Now molecular orbital theory, that means we need to write the order. Okay. Let's write. Let's write the first for the what? You have NO, right? For NO, you got how many nitrogen? 7. Oxygen you got how many? 8. Together you have a 15 electrons. Now if you write the order, let's write the MOT order for 14 electrons. That means still nitrogen. What was the order? Sigma 1s, sigma 1s star, sigma 2s, sigma 2s star. Then what do you have? You have a sigma to pz, pi to px is equal to pi to py. Then you have a pi to px is equal to pi to py star star, and lastly you have a sigma to pz star, right? That is the order till nitrogen. Now till nitrogen, that means you can find out the carbon C2 bond order also from that. Now C2 means how many electrons do you have for C2? 6 plus 6, right? You have a 12 electrons. So how 12 electrons can be distributed? Let me write here. It might looks a little bit messy, but you need to pay attention why and how I'm writing this. For C2, you got 2 electrons here, 2 here, 2 here, 2 here, 8, 10. I think this order is like, it might be reversed. Let me see. 5, 10, 11, 12. No, this is for the 16 electrons. Sorry, my bad. This is for the 16 electron, 10. Then you got 12, 14. Yes, this is for the 16 electrons. For the till N2, you have another order. I mean, everything remains same. Only this thing gets swapped. What gets swapped? Pi to px comes before the sigma 2 pz till nitrogen. Yeah. So sigma 1s, sigma 1s star, sigma 2s, sigma 2s star. Then you have a pi to px is equal to pi to py. Then you have sigma to pz. Then you have a pi to px is equal to pi to py. Both of them are anti-bonding star. And lastly, you have a sigma to pz. So for C2, 12 electrons are there, right? So 2, 2, 2, 2, 8. Then you got 2 here, 2 here. Total 12 electrons. So what is the bond order? Bond order for C2 has to be, how many electrons are there in bonding? We know the formula for bond order, right? It is number of electrons in bonding minus number of electrons in anti-bonding divided by 2. So you have how many electrons in bonding? You got 2, 2, 4 plus 8. You got 8 electrons in bonding. In anti-bonding, you got 4 electrons. 8 minus 4 divided by 2. 4 divided by 2 is equal to, that is for the carbon. Okay, chalo. That is for the carbon. Then what is another? O2 1 minus, right? O2 1 minus. The O2 1 minus, each oxygen has 8 electrons. So 2 oxygen will have a 16 and O2 1 minus will have 17 electrons. So how can you distribute 17 electrons? See here. Let me write it here. O2 1 minus here. So 2 electrons, 2, 2, 2, 10, 12. Then you got 15, 16, sorry, 2, 2, 2, 10, 10, 12. Then you got 14. Then you got 15, 16, and 7. So what is the bond order for this O2 1 minus? How many electrons are there in the bonding? Bonding are there this 2, sorry, 2 to 4 plus this 2, 8. Oh, sorry, this 2 to 4, 4 plus 2, 6, 6 plus this 4, 10. So 10 electrons are there in bonding. How many are there in anti-bonding? 2 to 4, 4 plus this 3, 7. So 10 minus 7 divided by 2. 3 divided by 2 is equal to 1.5. That means bond order of O2 1 minus has to be lesser than the C2. So where it is that? O2 1 minus, so you have that here. O2 1 minus lesser than C2. Here C2 is lesser than O2 1 minus. That means this is wrong. Here O2 1 minus is larger than C2. This is also wrong. Here you have O2 less than C2. That means it could be either C or D. So till C2 and O2 1 minus we are done. Now He, helium. Let's do it for the helium. Now helium, atomic number of helium is how much? It's 2. So you got what they're saying, He2 1 plus. So He2 1 plus, that means total electrons are how many? One helium is having 2, 2 heliums are having 4. You have 1 plus charge, that means 4 minus 1, 3 electrons. How can you distribute 3 electrons? 2 electrons in sigma 1s, 1 electrons in sigma 1s star. So bond order for He2 1 plus has to be 2 minus 1 divided by 2, which is equal to 1 by 2. That is equal to 0.5. That is equal to 0.5. So 0.5 is obviously lesser than the O2 1 minus. Technically it has to be the last, which is again last in C and D, both the option. Now we haven't got the answer yet. Okay, He2 1 plus is smaller than O2 1 minus. O2 1 minus is smaller than C2. That is present everywhere. Now we need to make sure that NO, if is the NO having larger bond order than C2 or not. Once we get that, we'll get our answer. Okay, NO total has 15 electrons, right? So when you have 15 electrons, you need to follow the order of MOT, which is having electrons more than 14. That is same order that we use for the oxygen also. Okay, so for NO, how can we distribute? It is NO, it is only NO, no? Yeah, 15 electron. How can we distribute? It is 2, 2, 2, 4, 8, 2, 10. Then you got 12, 14, and single electron here in 15. Single electron here. So for the NO, bond order has to be how much? How many electrons are there in bonding? 2, 2, 4. 4 plus 2, 6. 6 plus this 4, 10. You have 10 electrons in bonding. How many electrons do you have in anti-bonding? 2, 2, 4 plus this 1, 5. So 10 minus 5 divided by 2, which is equal to 5 divided by 2. And it has to be 2.5. So 2.5 is the correct answer. That means, and for C2 we know, for C2 bond order was 2. That means bond order for your NO has to be larger than C2. That is why the correct answer is D, where you can see the bond order of NO was larger than C2. That is why C is wrong and D is correct. Okay, that is how you can use the MOT to solve the different types of numericals. Moving ahead, which is most ionic here? Now, what compounds are most ionic? See, you need to look at the oxidation state of a element which is bonded with the oxygen. Okay, so ionic character is inversely proportional to oxidation state of an element. Higher the oxidation state, smaller is the ionic character. Smaller the oxidation state, higher is the ionic character. And it is inversely, for the covalent character, it is opposite. Covalent character is directly proportional to oxidation state of element. That means higher the oxidation state of an element, higher will be the covalent character. So since it is directly proportional for a covalent character, for ionic character, it is the other way. For P2O5, phosphorus oxidation state is +5. For MnA2, oxidation state of manganese is +2. CrO3, oxidation state of chromium is +6. And here manganese is in +7. So answer is right in front of you. In MnO2, manganese is having the lowest oxidation state, and that is why it should have the highest ionic character. Okay. Next, among the following orbital bonds, the angle is minimum between. Now we know that for Sp3 bond angle is 109 degree. For Sp bond angle is 180 degree. For HOH bond angle is 104 degree. Now between Px and Py, what is the bond angle? So if you write the Px, it has to be like this, and Py has to be like this. What is this bond angle? This is equal to 90 degree, right? So it is clear right in front of you that the bond angle has to be minimum in Px and Py orbitals. Okay. Lastly, last question. The correct order of increasing bond angle, XOX is, where your X is hydrogen, fluorine or chlorine. Okay. Now see, as the size of atom which is attached to oxygen increases, as the size of atom which is attached to oxygen increases, the bond angle also increases. That means if you have a bromine here, this is the bond angle of bromine, then you have a chlorine, then you have a fluorine. So if you write the bond angle, this bond angle has to be largest, then this, then this. That's the correlation between bond angle and the size of atoms which are attached to oxygen. Okay, so Cl2O has to be having the higher bond angle than the F2O. Now how many options are having it? This option is having opposite of that. That means this has to be wrong. This option is also having opposite of that. This has to be wrong. Now what we are remain with? H2O, Cl2O, F2O. Either this is correct or this is correct. Now for that we also need to find out the bond angle of H2O. See what happens in H2O and OF2. This is H2O. This is OF2. See, between oxygen and hydrogen, we know that oxygen is more electronegative than hydrogen. Then what happens? These bonding pair electrons are drifted more towards the oxygen. Since it is drifted more towards the oxygen, there is a large repulsion between bonding pair and the lone pair of oxygen, which makes this bond angle slightly larger than the OF2. Why? In OF2, we know that fluorine is the most electronegative element in the periodic table, right? It is obviously more electronegative than the fluorine. So what happens? This electron density is drifted more towards fluorine. Now, since this electron density is drifted more towards fluorine, the the bonding pair is shifted or drifted more towards the fluorine here, which is making the bond pair and the lone pair of oxygen. So, which makes the distance between this lone pair of oxygen and bond pair of OF2, the distance between them increases. When that happens, the repulsion between them also decreases. When the repulsion decreases, why? To increase the bond angle. That is why the bond angle is lesser in OF2 than H2. That is why the correct answer is Cl2O, then you have a H2O, then you have F2O. That means A is wrong and correct answer is B. Okay. That is how you can solve the different kind of questions, okay, by taking or by considering all the factors of the chemical bonding chart. Okay, that's it for today. Thank you for your patience. We have finished the second session of our NEET crash course 2021. Okay, in the next session, that is the third session of your NEET, we are going to cover the chapter called structure of atom. Okay, that's it. Bye bye everyone.